Venkatesha. So he's a UGC assistant professor and program director of physics in the School of Physical and Applied Sciences at Goa University in India. He completed his PhD at the Indian Institute of Science in Bangalore with Guru Rao in 2011. And that was followed by two postdoctoral research positions, one at University of Augsburg in Germany with Wolfgang Scherer, and the other one in Aarhus University with Bo Iversen. Prior to joining Goa University in 2018, he was an assistant professor at the University of Tsukuba in Japan with Eiji Nishibori. So his current research interests include the synthesis of multifunctional materials, quantum crystallographic studies, and crystal engineering. He's an expert in single crystalline powder X-ray diffraction, also neutron and synchrotron diffraction, and obviously electron density analysis using the high resolution data. He's presently applying this expertise to study photoluminescent and photocatalytic materials, also phase transitions and hybrid halide perovskites for energy applications. And he is, as the title also suggested, an expert in the analysis of weak intermolecular interactions towards the structure property correlation using quantum crystallographic methods. He's also a recipient of the ASCA Rising Star Award from the Asian Crystallographic Association, and currently he serves as a co-editor of the Journal of Applied Crystallography and as the deputy coordinator of the Materials Characterization Laboratory at Goa University. And with that, I am done. And dear Venkatesha, the screen is yours.
Thank you very much. First of all, I would like to thank Professor Christoph, Professor Paulina, Professor Anna for inviting me to and giving me opportunity to present under distinguished lectures on quantum crystallography and complementary fields. I have been working in this area of weak interactions and charge density analysis over past 15 years or so. So I would like to share some of our results from past and present work. Before going to my title, let me briefly tell about my working place, Goa University in India. I think many of you know about Goa as a tourist destination known for beaches and waterfall. But there is a other side of the story also. For example, Goa University is quite young and small university. It started in 1985. This is a unique place for master and PhD degrees in foreign languages like French, Portuguese, and Konkani is a local language of this state, and offers certificate courses in Japanese and Spanish languages. Also, we have like 6 research institutes, for example, Goa University, IIT Goa, NIT Goa, BITS Goa, also National Institute for Ocean Research, also Polar and Ocean Research. So like quite a cluster of universities within 30-kilometer radius. So we are here west coast of India as a very small state. Actually, it is the smallest state in India. You can't see in the map maybe. This is our department, School of Physical and Applied Sciences. Here we have single crystal XRD, 2 powder diffractometers like rotating anode and smart lab to do all kinds of crystallographic work and material characterization. This is my group, quite small group. So we are putting our map in the crystallographic community. Let me go to today's presentation. We know that all materials are made up of atoms, ions, or molecules. They are actually building blocks. For example, now I am speaking on organic crystals, so I will take molecules as building blocks. Now, if you arrange these materials in a 3D arrangement, we will get crystals. So basically, you are arranging different all molecules in periodicity. So this brings the point of close packing. So once the molecules are recognized each other, they develop like intra and intermolecular interactions. So these interactions are very crucial for conformation of the molecule and close packing of the molecules in the crystal. Now, these intermolecular interactions can be like predictive, like for example, this is called supramolecular synthon. For example, if you know the carboxylic acid functional group is there, there is a possibility of getting acid-acid dimers. Or if you have acetamide kind of molecule, then you can predict amide-amide dimers. So these are kind of now molecular modular building blocks. So they will be used to develop new kind of solids. For example, this is a field called crystal engineering or supramolecular chemistry. So if you know the functional groups, you can tune their energy, you can tune their interaction. So this will lead to different type of properties like polymorphs, co-crystals, etc. Now, these weak non-covalent interactions, they directly influence properties of wide range of research areas. I have highlighted few because of space. For example, they are well known in pharmaceutical solids. They will give polymorphism, like how they are arranged in the crystal. Then they are also very important in framework porous solids. So if you change the functional groups, you can alter the pore of your solid. They also play very important role in chemical reactivity. For example, photodimerization, we can control by pi-pi interactions or something. Host-guest interactions, for example, this whole research area is depending on this weak tuning the strength of weak interaction. Also, we know that drug delivery, for example, protein-ligand interactions, also stimuli responsive system like bending of the crystals or molecular machines. All these properties can be controlled, can be tuned by changing these weak intermolecular interactions. Now, there are different types of non-covalent interactions depending on donor-acceptor atoms. They are involved in the chemical bonding. Also, their energies, for example, you can classify into different categories. For example, well-known non-covalent interactions are like, for example, hydrogen bond, halogen bond, tetral, chalcogen, nicogen bonds are there, pi stacking interactions are there, then several van der Waals interactions are there. Now, for example, what kind of atom is participating in the intermolecular interaction based, then you can classify into different classes. Also here, energy plays very important role. For example, very strong hydrogen bonds are there. Their energy ranges from 15 to 40 kilocalorie per mole. Then strong hydrogen bond, weak hydrogen bonds are there. Whereas kind of like weak hydrogen bond, pi stacking interaction, halogen bonds comes under very weak interactions. Their energy may vary from like 1 to 10 kilocalorie or depending on their interaction geometry. Then these weak interactions play a very crucial role in organic solids. My supervisor, Professor Guru Rao, he used to describe them as Gulliver effect in organic solid. I think all of you may know the story of Gulliver's Travels by Jonathan Swift. He is a giant person. He landed up in a country of Lilliputs. They are tiny people, but they could arrest him by using like small porcels, like for example, tying their hairs, tying his hand, legs, etc. So here, even though they are tiny people, they could tie up a huge person like Gulliver. This is a rough approximation. It may not represent exactly, but total strength of these tiny interactions sometimes may exceed like strong interactions in the molecules. So for example, you can see right hand side, there are several cooperative interactions are there. These small interactions may control the molecular geometry properties. sometime play the important role. So here, a small disclaimer, I am using this Gulliver thing to explain role of weak interactions, not in any other context. So there are different ways of evaluating these interactions. In early days, for example, geometrical criteria was used to describe these interactions. There is a kind of thumb rule is like, for example, bond distance between two atoms is less than van der Waals distance, or bond angle is roughly greater than 120 degree, then we used to classify as some kind of interactions like hydrogen bond, etc. Then there may be like we can use chemical intuitions, for example, electrophile, nucleophile type of interactions. This will lead to existence of chemical bonding. Additionally, we can use several methods like spectroscopic methods, like Raman, other techniques. Computational methods also we can use. Then obviously we can use quantum crystallographic methods to prove that existence of different chemical bonds in the solid. Now I will explain very briefly X-ray charge density methodology for the sake of completeness. For example, in routine structure, we use spherical electron density. This is described as core and valence electron density. This is useful to solve the crystal structure. Then it does not account all bonding electron density. We can see that there are left out residual densities in the bonding area. Nowadays, we can use non-spherical form factors. For example, no sphere A2 in OLEX is available, so we can improve our structural refinement. Whereas, if you collect very high resolution data, then we can use Hansen-Koppen's multifold formalism. This takes care of refining atomic density into spherical and aspherical part. This aspherical part will take care of the bonding density. So to perform experimental charge density analysis, we should have good crystals. They could diffract like high resolution. Typically, we need sine theta by lambda about 1.1 angstrom inverse. So nowadays, this is very easily available. Also, as the quality of the data increases, we can extract more information. So once we have good charge density model, we can do the topological analysis using Bader's quantum theory of atoms in molecule. Then we can estimate atomic charges, interaction energies, lattice energy, electrostatic potential. So many other properties related to electron density can be calculated. So in the case of hydrogen bond, this is well established, or there are several papers are available by applying charge density methods. The well-known, some of the examples I am highlighting here, for example, Koch and Popelier criteria is used. Koch and Popelier proposed 8 criteria to establish weak hydrogen, for example, CHO interaction. Now, this is well used to classify all kind of hydrogen bonds. Then there is a additional work, like for example, what happens when you are dealing with strong hydrogen bonds, like resonance assisted hydrogen bond. They can also classify and study them. Then another work is from Espinosa. The relation EML relationship is quite used to quantify strength of hydrogen bond by using potential energy density at the critical point. Afterwards, I think there are several papers are available to understand topological properties. This is quite used to study, classify different regions of the hydrogen bond. For example, strong hydrogen bond, weak hydrogen bond, van der Waals interaction. This is done by, for example, Professor Espinosa, Professor Guru Rao, and Professor Munshi have done quite a work in the classification of hydrogen bond. So I am not going further in this direction. I will now move to halogen bonding, where I perform some experiments. Here, halogen bonding is nothing but non-covalent interaction where halogen acts as a electron density acceptor. Here we have different halogens we can consider, for example, iodine, bromine, chlorine. Also nowadays, fluorine also considered as one of the halogen involves in halogen bonding. So we concentrated basically on like two similar halogens, why they interact or why they come together in the close packing of molecules. For example, if you look at the structural database, there are basically two type of halogen-halogen interactions are there. Is classified as type 1, that is theta 1 is equal to theta 2, that is an angle between CXX and XXC. This angle is, if it is equal, then it's called as type 1. Then further, this can be classified as trans geometry. If it is like in the trans across the inversion center, then it can be in cis geometry also. For example, if it is across two-fold symmetry. Then there are type 2 interactions where theta 1 will be very linear, like 180 degree, theta 2 will be in 90 degree. So some questions to answer is why two identical atoms come closer. For example, they are quite electronegative atoms. Then additionally, there are many active pharmaceutical ingredients, for example, API. They contain halogens, especially chlorine and fluorine. So they improve the bioavailability and all those proper chemical properties. So there are models available to explain this type of halogen interactions. One is Newborg model. He suggested there is a polar flattening effect on the halogen bond. For example, along the CX bond, there is a depletion of the electron density. Then there is a accumulation of the electron density perpendicular to the CX bond on the halogen atom. So this decreases repulsion between two atoms. Similarly, there is a Williams model. I think here electrodeficient region, like charge deficient region, is concentrating on the charge accumulated region. So this makes like partially delta plus delta minus type of interaction. So they are quite attractive in nature. Then we try to understand this halogen-halogen interaction by taking chlorine as an example. Here we have taken three organic molecules where we can see type 1 trans geometry, type 1 cis geometry, and type 2 L geometry. So here distance between two halogens are within the sum of van der Waals distances, and angles also satisfies type 1, type 2 criteria. Then we have done the experimental charge density analysis, also coupled with theoretical calculations. We can see that whatever proposed, like polar flattening effect on chlorine atom, we can clearly see in the static electron density that red region is charge depletion region on the chlorine atom, whereas blue region is charge accumulation. So this polar flattening effect or anisotropic distribution of the electron density decreases the repulsion between two halogens. That is the reason they try to come closer in the close packing. Similarly, if you look at type 2 geometry, as Williams model suggested, here you can clearly see the electrostatic type attractive interaction because charge depletion region is directly facing the charge accumulated region. Here, there is a Espinosa also published similar geometry. Here, he worked on X3 geometry. Here, you can clearly see three chlorine atoms are coming together in the X3 synthon way. So these all kind of interactions, if we study, we can say that, for example, there is a decreased repulsion because of polar flattening effect, and type 2 geometries are definitely attractive in nature. Then we extended this interaction to other geometries, like for example, what happens if you take heterohalogen in the case of, for example, chlorine F interaction. Here we could see very tiny polarizability on the fluorine atom even in the experimental charge density analysis, but the extent of polarization is very small in fluorine. The reason is it is very small, it is very highly electronegative element among in the periodic table. Also, we extended to fluorine-fluorine interactions, then ClO type halogen bond, then CHF in hydrogen bonds by using CF3 as a like functional group. Everywhere we can see that there is a reduced repulsion due to polar flattening effect. Even we can see tiny polarizability on fluorine, organic fluorine, though it is very small. Then type 2 interactions are definitely favorable over type 2 geometries in organic molecules. Then we proposed like supramolecular synthons are there. They are modular units and robust. For example, if you have carboxylic acid functional group, then you have probability of having acid dimer is more. Similarly, amide group will give like NHO type of infinite chain. So here plan is like this synthon or modularity of these interactions we can use for the transferability of multipolar parameters. For this we have taken two molecules to get, for example, molecular 1 we are getting carboxylic acid dimer synthon, whereas in the molecule 2 acetanilide, here we can get amide infinite chain. So we use multiple parameters from 1 and 2 to synthesize the third molecule. It is having both carboxylic acid dimer and amide chain. So this we actually compared with experimental, for example, this is a molecule 3 after transferability. We can compare our transferable topological parameters with experimental charge density parameters, also theoretical charge density. They are quite comparable and quite reproducible, so that we can apply this transferability things for like routine structure and get charge density features. So in the next one, we thought of extending this work, for example, to correlate properties. So in this case, we have taken organic semiconductor, rubrene. This is well-known compound. For example, it has highest mobility among organic molecules or organic compounds compared to other counter organic molecules. For example, pentacene is having 2.2, whereas rubrene has like 10 times higher mobility. This is a case where what is the reason rubrene is having higher mobility compared to other molecules? The primary reason is pi-pi stacking interaction. So this favors the charge transfer between two molecules. That's why we observe higher mobility. But obviously their mobility is smaller compared to, I think, well-known silicon. It is known for semiconductor industry. So now, for example, tetracene having lower mobility. The reason is you can see it is not having pi-pi interactions. Instead of it is having CH-pi interactions. Whereas if you go to rubrene, we can clearly see overlap of this tetracene backbone in the crystal structure. So this favors the charge transfer between two layers. So there are different polymorphs also available. For example, orthorhombic, triclinic, monoclinic. Triclinic and monoclinics are not very good. Reason is they are having CH-pi interaction. It means the tetracene backbone is not perfectly overlapping. Whereas in the case of orthorhombic, we can see the overlap of pi-pi rings. Now this compound is kind of like reference molecule. We collected both X-ray data and neutron data, neutron diffraction data at 100 Kelvin. Then we compared delta U values, there is between thermal parameters of X-rays and thermal parameters from neutron data. This is one of the compound we can see minimum delta U values even at 100 Kelvin compared to other organic molecules. Similarly, then we compared whatever obtained delta U values with other methods like multipole method, shade, HAR. Then we can even from the experiment we can get very comparable delta U values like whatever obtained in shade and HAR method. Then from charge density analysis, we could show that there is a bond path between pi-pi tetracene backbones. Then we can see the critical point between pi-pi interaction. This is also seen in reduced density gradient isosurface. So this proves that there is a kind of pi-pi interaction between two layers. Then this is also coupled with very weak HH interaction, because there should not be any repulsion between two adjacent phenyl rings. So this also kind of compensated by short like HH bonding in the rubrene molecule. So the presence of phi stacking interaction was established by charge density analysis. Then we have taken example of another co-crystal here, phenazine chloroanic acid co-crystal. This is well-known ferroelectric material. For example, you can tune the property of ferroelectric phase transition. For example, if you change the halogen atom, for example, fluorine is not showing any ferroelectric transition. Similarly, iodine is not showing any ferroelectric property. Whereas chlorine is having transition temperature about 253, bromine is little lower, 138. For example, if you have a mix of chlorine and bromine, as expected, you have a transition temperature in between. Now they show very excellent properties, like there is a shift in transition temperature if you change from hydrogen to deuteriation. So you can see transition temperature is increased. So we want to see whether the main reason for this type of property is OH-N hydrogen bond. This changes as a function of temperature. So for example, this is ferroelectric, paraelectric at room temperature. You can see the space group is P21 by, it is centro-symmetric space group. So we have half of the molecule in the asymmetric unit. So we have OH and hydrogen bond, this is perfect. Whereas if you go to ferroelectric phase, that is after phase transition at lower temperature, this hydrogen bond is like elongated. So there is a movement of protons. This results in breaking of the inversion center. So this results in non-polar space group P21. This also we can see by like ADPs of hydrogen bond. There is something happening with one of the hydrogen. So we also saw the packing diagram. We can see that in the paraelectric phase at room temperature, there are intermolecular interaction that will be now divided or split into two parts because of the breaking of inversion center. For example, OH and hydrogen bond is there at ferroelectric phase. Then we get two distinct hydrogen bond. One is usual hydrogen bond that is comparable with the paraelectric phase, whereas elongated hydrogen bond will be like the distance between oxygen and hydrogen will be very high compared to the. So here proton is moving or moved as a function of temperature. Then we also explored this one using Crystal Explorer. We can see or we can calculate energy of this OH and hydrogen bond. In the case of paraelectric phase, as expected, these both are symmetric. For example, their energy is same. Whereas in the ferroelectric phase, their strength is different now. One is kind of around 35 kilojoule, but whereas other one is now almost double. So this falls under like hydrogen atoms are known to have this type of things. For example, usual hydrogen bond, hydrogen will be in single potential, like it is at the lowest minima. Whereas in the low barrier hydrogen bond, it tries to move between two acceptor and donor atoms. Whereas in the case of like disordered hydrogen bond, it may be like shallow potential is like locked in the shallow potential so that it occupies both positions. If it is a short hydrogen bond, then hydrogen will be very symmetric between acceptor and donor. There are few studies on this type of interaction. For example, Bo and Finn Larson have studied this type of very short hydrogen bonds in organic compounds. Now, if you look at this compound, it has nice phase transition, actually several phase transition. First one is paraelectric to ferroelectric. Then it has incommensurate phases. You can see appearance of tiny peaks, satellite peaks. Also, it goes to very complicated structure at very low temperature. So here, if you want to explore our ferroelectric phase 1, we should be in above 150 Kelvin. So this is little tricky for experimental charge density analysis because the temperature is relatively high. But we collected experimental data using synchrotron facility at Springate, Japan. Also, it was a little tricky because now weak reflections are emerging due to breaking of inversion center. Also, we can't go low temperature because there is a modulated phase or incommensurate phase between below 147 Kelvin. So also we should have neutron data also. Otherwise, it's very difficult to model the hydrogen atoms in this case because there is a hydrogens are behaving very different in the ferroelectric phase. So we could do the experimental charge density analysis. In the one of the hydrogen is, as I mentioned, is usual normal hydrogen bond. So this behaves as a usual hydrogen bond. You can see electron density and Laplacian value suggest that this is a usual hydrogen bond. If you go to low barrier hydrogen bond, now we can see that the electron density between like OH or NH bond is drastically increased because of this one. Also in the intermolecular space also, we can see that there is a considerable electron density is there. Also Laplacian is now like indicating that there is some kind of covalency when it is elongated or when it is tried to transfer to another atom. So this also coupled with theoretical calculation, there is quite correlation between experiment and theory. So we can show that there is a low barrier hydrogen bond that plays very important role in the properties. These are topological parameters. We did theory, multiple theory, topon, amol calculation in the gas phase, also in the crystal phase. So then we can compare all these topological properties to correlate the whatever property we observe. And also we did phase, paraelectric phase. Actually, this is at room temperature or relatively high temperature, about 250 Kelvin. So only theoretical model we could do. Then we can see that here OH and hydrogen bond acts as a usual hydrogen bond if you see the electron density and all these parameters. So we can partially proton transfer is observed in the ferroelectric phase and hydrogen bond is characterized as low barrier hydrogen bond. Next, I will take the example of perovskites. We are familiar with the usual oxide perovskite. It is having AbO3 formula. Here A site is the black one, then BO6 octahedra will be there. This is a corner shade. Now, if you move to halide perovskite, we are replacing oxygen with halides like chlorine, bromine, iodine. Then this A site, for example, we can occupy with the inorganic ions like cesium, rubidium, or we can replace with monoatomic like monocharging, like organic molecules like amines and all those things, then this halide perovskite becomes hybrid material because it has now both organic, inorganic layers in the structure. But here property is depend, or because we can now play with the A side, you have lot of molecules are there. X is also now variable, but this all structure perovskite property is depending on Goldman's tolerance factor, depends on radius of A site, radius of B site, and radius of the halogen atom. So we can end up with like cubic perovskite, tetragonal perovskite, orthorhombic perovskite, or you can have different dimensionality like 3D, 2D, 1D. Also, you can have double perovskite or triple perovskite based on these cations. We are working on this area, for example, haloid perovskite or hybrid halides. We can use them as efficient photocatalysts. Recently, we published this paper with cesium-2Ag bismuth Cl6 in the crystal growth and design as a front cover. It shows excellent photodegradation property, like within 10 minutes, it degrades all the pollutants present in the our reaction. So then in the next case, for example, here cesium-2 sodium iron chloride, it shows reversible thermochromism. Actually, here structure is not changing as a function of temperature, but we can see clearly the change in the emission properties. Similarly, you can tune the photoluminescence. For example, we can play with the A site, we can play with B site, we can play with halogens. So this gives different emission properties. Also, there is a phase transition. For example, if you have layered material like 2D perovskite, then we can clearly see that they undergo phase transition. So I will take the example of 2D layered halide perovskites. There we could see the phase transition. For example, ethyl ammonium manganese chloride and ethyl ammonium cobalt chloride. Actually, we synthesize other series also like copper, zinc, and all those things. But these compounds are very sensitive to air and moisture, so it's very difficult to crystallize them, also to collect the data. So we concentrating on these two compounds now. We can see that there is a phase transition in DSC plots, also dielectric measurements. We can see clear phase transition. TC is in the case of manganese about 210 to 220 Kelvin. Here at the room temperature, it is in the, or before phase transition is in the tetragonal phase, it goes to orthorhombic phase. This is characterized by, you can see that there is a disordered organic site or organic molecule or ethyl ammonium molecule. So this represents the dynamic state, whereas it will be frozen if you go to the lower temperature. Whereas in the cobalt case, phase transition is about 220 Kelvin. Here also it is disordered ethyl ammonium, and this phase transition is orthorhombic to orthorhombic, but it is now centrosymmetric to non-centrosymmetric. So basically at lower temperature, symmetry reduces and becomes more ordered structure. But one point is here we can't compare these two things. The reason is one is perovskite structure because you can see corner shaped polyhedra, whereas in the cobalt case this is a now 0 or 0D, or it is 2D, but they are not connected as in the case of perovskite. So we also measured magnetic properties, but problem with the magnetic properties, they are not correlated with the structural phase transition. For example, in the case of manganese, they are antiferromagnetic to canted ferromagnetic transition is there very low temperature like 40 Kelvin, whereas in the case of cobalt, it is paramagnetic throughout the all temperature. So there is no correlation with the magnetic property with the structural phase transition. We could do charge density analysis on both these compounds. Here we can see that this, even though we can't compare directly because their structure is quite different. So, but we could see that metal halogen bonding is more ionic in the case of manganese case or in the perovskite case, whereas in the case of cobalt, that cobalt Cl bond is less ionic compared to manganese case. So we could see quite a lot of NHCl interactions are there. They show that like chlorine is like having a polar flattening effect and facing the hydrogen atom. So they are quite electrostatic in nature. So in summary, we can say that role of weak interactions could be quantified by topological properties of electron density. For this type of studies, we should have very high resolution data and good crystal so that experimental result can be correlated with like maybe qualitatively with properties. We know that there is no direct quantitative relationship between physical properties of material and electron density. So as of now, all these things are, we can establish a qualitative link between property and structure using electron density features. Then experiments are really required in the case, even in the case of organic molecules. These are two kind of examples. For example, phenazine, chloranilene, co-crystal, we know that it undergoes several phase transition like incommensurate. So these things, unless we can't, unless we do the experiment, we may not be able to see all this. Similarly, this is a well-known example from Bo Everson. Here, titanium disulfide is there. Here, sulfur-sulfur bond is showing more covalent features as instead of like purely van der Waals in nature. So I think experiments coupled with the theoretical calculations really required to see unusual and surprising results. So these are some papers I suggest for younger students. There is a debate when to consider to context as interactions, when to consider this as a just a like geometrical contact. So I think I suggest to go through these papers. Also, there is a paper from Professor Speckman related to how this topological properties can be correlated with the energy of the hydrogen bonds or any interaction. So with this, I will come to acknowledgements. I would like to thank all my mentors who introduced to me this charge density field, weak intermolecular interactions, Professor Guru Rao, Wolfgang Scherer, then Iverson, Professor and IG Nishimori. They shaped me what I am today. I also thank all my collaborators. They are part of my work at various stages, like Professor Munshi, Professor Chopra, Professor Kundu, Professor Bobe, and Professor, Dr. Reddy from UGCDAE Center. Also, I thank all my students, funding agencies, and Goa University for all the support. Thank you for your attention. So I am happy to answer if there are any questions. Yeah. Thank you.
Thank you very much, Venkatesha, for a very interesting and clear lecture. We already have some questions. I will read the first one. A question from Vikas. Which type of hydrogen bonding potential well do we observe in the case of single component hydrogen bonded systems that follow the proton tautomerase mechanism in a ferroelectric and paraelectric phase, such as in imidazole-based ferroelectric system?
Okay, in the para-electric phase, that is before phase transition, we are using finding usual hydrogen bonding potential well, like one minima is there, it is bound in that minima. Whereas if you go to other case like ferroelectric phase, now hydrogen is elongated or it is shifted. In this case, we are seeing low barrier, like the potential is too shallow wells are there. They are like trying to move or kind of low barrier potential. Yeah.
Thank you. Another comment from Elżbieta Bartoszak-Adamska. Thank you for the valuable lecture. And the next question from Uli Englert. Thank you for the nice and informative presentation. You have shown us the pi-pi interactions in rubrine. in the Bader analysis, this was associated with a rather curved bond path. In your experience, is such a curved bond path a good indication that the intermolecular interaction is weak?
Okay, I think I did not mention, but we had very high quality data in that case. For example, in the case of rubrine, it was collected in Springate. The resolution is 1.64 angstrom inverse. So we could deconvolute really well all the thermal motion and electron density features. So whatever we could see is, I think, real, because we can see same thing in other things like reduced density gradient also. I suggest to read through that last slide. So there are 3 papers that debated heavily on this topic. I suggest to go through that one. Yeah.
Thank you. Arista Bolivar Wufak is thanking for the presentation. Okay, I do not see any other. Yeah. Okay, Anna, please.
Thank you very much for the presentation. I take the chance because someone is typing, so I can ask a question. So if I understand correctly, of course, organic compounds usually have much higher output in properties if you compare it to inorganics, but obviously mechanically, this is a drawback. And then you present the perovskite, the hybrid perovskite systems, which I understand you combine then the mechanical stability with the, let's say, vast property. So have you thought, for example, to expose those compounds into not only temperature as a stimuli, but also pressure, and to see how actually mechanically they are stable?
Yeah, I think definitely this is a good suggestion, I say, because they should undergo same type of phase transition or things under pressure too. But one problem, this type of compounds they are really unstable. Means main reason is we are using A site as like some organic molecule, or that is normally amines, because they come with +1 charge or something. So they are very unstable even during synthesis. Also, quality of the crystal is very bad. Actually, we thought of doing magnetic property like Piero Macchi does, like he want to correlate d orbital population with the magnetic property, but quality of the data is not good enough to do such things. Yeah. Mainly, these materials, as I suggest, is very sensitive to synthesis as well as exposure. Yeah.
Thank you.
But definitely we should look. Yeah.
Christoph?
When I was younger, I was studying a lot so-called proton sponges and proton sponge complexes, where proton was going in between 2 nitrogen atoms. And at that time, it was a moment that we were thinking about so-called pi H plus pi hydrogen bonding. And rubrine is an excellent example. And we were not successful, but maybe you could be better successful to create like rubrine salt with proton, which is in between the 2 rings. That would be quite something. Have you thought about this kind of?
Okay, we will definitely try kind of this. Very interesting suggestion. Yeah, thank you.
Welcome.
We have now more questions. A question from Harita Mambata. What software do you use for these studies?
This means I did not.
What kind of software program? You used Mopro, XD, Yana?
So I use XD recent version for all multiple refinement. Then for theoretical calculation, Crystal we use for like Topond. Then for gas phase calculation, like Gaussian for usual one. Yeah. Like AMOL is done using the Gaussian output. Yeah.
A question from Arista. Do SOMO orbital may influence magnetic properties through halogen or hydrogen bonding?
Could be, because they show different properties. For example, whatever two examples I have taken, their magnetic property is completely different. One is paramagnetic throughout these things. Another one is showing antiferro to ferro transition. So I am not able to comment or say anything at the moment, but they are very complicated molecules.
And from Sabam Gavas, great presentation. I have one more question. You have many systems with phase transition, and you commented that it's very difficult or almost impossible to get charge density data at room temperature. Do you have any ideas what we would need to improve, or in which direction to go to get such information at room temperature?
Okay, I think in terms of theoretical calculation, I think no spare now A2 is there. I think that is gives excellent non-spherical form factors. I think we can do quite a lot. In terms of experiment, I think it's very difficult, because main problem is our scattering factor drops. Then I think we may miss all high resolution data. So.
But even better detectors? I don't know.
Yeah.
Piero, Maki, room temperature, charge density is possible. Everything depends on the dBi T of the materials. Yeah, sure. Yeah, but it's far more difficult.
The more inorganic, the easier to get charge density done.
I think Pierre is correct. I think diamond is studied quite a lot. Even maximum entropy method, even at high temperature, if I remember correctly, Professor I.G. Nishibori and Bo Iverson, I think they studied even at relatively high temperature.
Further comments from Piero Maki. The T of materials decrease at high pressure, so that's another way to go. Yeah, but then it's no ambient condition anymore.
Yeah.
Increase.
Yeah, thank you for information. Yeah.
And from Vikas, will electron diffraction data help in the case the crystals are not stable instead of single X-ray diffraction data collection? So it's about electron diffraction versus X-ray diffraction.
Here I will suggest Paulina to answer this question. You are a better person.
Probably depends what is the reason of the instability, because in electron diffraction you also have to prepare your sample for data collection. It takes time.
I think once we load these samples, I think while synthesis, if you control the parameters and if you get good quality crystals, once crystals are there, we know how to handle. It's not a problem. I think growing crystal is the problem here, I feel.
Okay, then for electron diffraction, you don't need to have huge crystals, so maybe the growing time can be much shorter, and maybe that's the way to go.
Yeah, that is. I do agree with this point.
But the quality of electron diffraction data for the purpose of experimental charge density studies or experimental electrostatic potential quantitative studies should be really incredibly good. I mean, at present, it's probably 1 per 100 crystals, 1 per 100 trials. So it's very rare case. So maybe Paulina is more successful. Maybe she's got 2 or 3 per 100.
It's about the quality of the experimental experiment. I think it's rather about the accessibility to the machines and to the software, which is also very time-consuming. I would say that the moment we are now in electron diffraction in terms of charge density, it's kind of similar as X-ray diffraction was 25 years ago, or
50. 50.
No, 15. It's not so bad, I think. And the speed of improvements, I think it's much faster. So I expect that in 5 years it will be really possible.
When more hardware will be distributed among crystallographers and bigger expertise is being used, so then will be a big progress. Agree.
A question from Ibrahima Goldiapi. For the Laplacian map, what software you used?
I think in my case, all these plots are done in XD, like XD prop we use.
For 2D maps, that was in...
three-dimensional.
Or no, but you haven't shown three-dimensional Laplacian, right? So the 2D Laplacian was XD prop to compute it and then to plot it. Which software you used to plot it? The one which is...
Yeah, 3D plots are done in Molkel.
And 2D plots, there is a software distributed with XD for 2D plots.
Yeah.
Yet another person is typing. From Vikas, I really enjoyed the lecture. It keeps us connected and updated with ongoing research. Thank you. Yeah, so that's excellent closing statement for this part of our seminar.
May I have the one, say, critical comment? I mean, I personally, the more we do inorganic crystals, I'm against this polyhedral representation, especially when we talk about electron densities, because it's very much misleading. I mean, if you have polyhedra, the polyhedral representation is good at the structural level, but we shouldn't use this at the level of electron density, because why not to use atomic basins, changes of atomic basins? That would be far more informative.
Yeah.
You have one more question from Shabam Gavas. How can structure property correlations reduce trial and error in materials selection for specific application?
Okay, I think correlation is like, for example, in the case of that phenazine and chloraniline co-crystal, we can play with, for example, halogens. We can tune the property. For example, we know that halogens are playing important role. Whereas in the case of, similarly, in the case of hybrid perovskites, for example, if you know the like some property, we can try to tune. Like if you know the structural inputs, whether we can change something and we can get some. I think some inputs we get, it may be perfect, or it's like at the end it's a trial and error only. Yeah.
Thank you.
And there are beautiful correlations of different properties with electrostatic potential by Politzer and Jane Murray. So it is possible to have a nice relation between properties of electron density or electrostatic potential and other properties of materials.
Yeah, that is true. Someone is typing.
Yeah, there's one more person typing. Let's wait.
They stopped. Oh, they continue. Maybe in the meantime, a bit provocative question. I mean, you're working with halogen compounds, but I mean, if you think about sustainable chemistry, everyone wants to go away from the halogens. Do you have an idea with what you could actually replace halogens to have a similar effect?
I do agree with your suggestion. Halogens means instability. Yeah.
But then, do you think about any other element or group of elements that actually could preserve a similar behavior, but be, let's say, more sustainable in terms of application? Do you have an idea?
We entered to this halide perovskite because they show excellent physics. For example, maybe they are not application oriented, maybe very difficult because their stability is still problem. But they display variety of properties, like you can go in any direction, you get one property. And you can play with the A side, B side, C side, you get so much structural diversity. I think it's like a good area to explore. Yeah.
Research why it is a nice playground. I absolutely agree.
Question, from Vikas. 2D peroxides are more stable than 3D. Could this be a rescue in terms of stability for the ferroelectric system?
I think generally this is true. For example, double perovskite, whatever I shown, that thermochromism, like crystal changing color, these all are 2D perovskites. They are stable like 6 months, 1 year, nothing will happen. So whereas 3D, like usual ABX3 perovskites, they degrade over the time. I think, stability is more in the case of 2D. I think if you go lower, further, they are quite stable. But sometimes they may not be perovskite. For example, if you go further, lower in dimensionality, they lose the perovskite property also. But one thing, 2D perovskites are not good in terms of property. For example, if you go to solar cell or photocatalyst, anything, I think 3D are the better. And lead one is the better, but lead one is like toxic. They want to replace it.
Okay, thank you once again for your lecture and for the questions and answers.
Thank you very much. It is my pleasure to be part of this lecture series. Thank you all.